Welcome to our BNMA webinar for February. Thank you very much, everyone, for joining. My name's Helen Mayfield. I'm a research fellow here at the University of Queensland, and I'm the current president of BNMA. So along with my fellow board members, some of whom I think are online, we're really excited that you guys could join us today for our first webinar. I do want to have a bit of plug of membership for the association. Thank you, Yue. So for those joining, we do have membership for the organisation. There's a lot of benefits to being a member. So we've got discounts to events throughout the year. The other benefit is that you can connect with world experts in the field. So a lot of the people who write the textbooks on BN are also members or associates of ours. So it's a great way to, if you want to reach out and if you've got questions. The other exciting thing that we're starting up is in the newsletter, we're going to be sharing people's research. So if you've got recent papers published related to Bayesian networks or causal modelling and you want to share those with other members, you can let us know, and we're now going to publish them in the newsletter and put them on the website. So it's a great way to get your work out there. Thank you, Yue. And now, without further ado, I will introduce our speaker for today. So, hi, Tom. We have Professor Tom Snelling, who's a professor, is the Director of Health and Clinical Analytics in the School of Public Health at the University of Sydney, and also an infectious disease physician at the Sydney Children's Hospital Network. His work includes applying causal modelling to the design of clinical trials, including management of cystic fibrosis and patients post-kidney transplantation, as well as primary prevention of allergy and treatment and prevention of COVID-19. More importantly, Tom has made a Bayesian network to help him diagnose why his 48-year-old car refuses to start. So I think that will be our first question. Tom, do you want to tell us a bit about that project?
Thanks, Helen, for the introduction. Yeah, so I've got an old Alpha that rarely starts as it's supposed to start, and I spend a large part of my time trying to get it to start. So, look, I'm trying to build a network model to help me diagnose the various things that go wrong. But as I build the model, I find more and more things that go wrong with this car. So it's turning out to be an extremely complex model. But if I ever get it working, I will be delighted to share it with other Alpha owners.
Excellent. Well, we wish you all the best with that. That does sound like a rather challenging issue. Okay, Tom, if you'd like to share your slides and begin your presentation.
Thanks, Helen. Thank you to the Society for the invitation to present. I might just say a little bit about the group that I'm involved in, Adaptive Health Intelligence. So we're a team that has really across Australia, but with two main nodes, the University of Sydney and the Telethon Kids Institute in Perth. But we also have a broad network of collaborators across Australia, including members of the BNMA. And really our work is in the application of Bayesian causal inference to various clinical problems and to health policy problems. We're a very multidisciplinary group. We have clinician researchers, we have modelers in our team. We also have a number of statisticians, but also we're supported by a team of implementation experts. These are project coordinators, IT support, data management, a range of other individuals with the expertise needed to get these projects off the ground. Our key applications are in comparative effectiveness studies, so comparing alternative treatment strategies for particular conditions. And we do this in a couple of different ways. One is through clinical trials, and the other is through observational studies. The focus of my talk today will be in our work in clinical trials. But we also do work trying to develop decision support tools. We're very interested in the broader concept of learning health systems, this idea that hospitals and health services should aim to learn about improved management of patients with every hospital encounter. And we also do work in pharmacovigilance and vaccine safety. But I'm going to talk about clinical trials and the relevance of Bayesian networks to clinical trials. And I'll start perhaps by comparing our approach with perhaps what is a more traditional perspective on clinical trials. I think a more traditional perspective is that trials are really a sieve for evaluating hypotheses, where the hypotheses are traditionally stated in the form of a propositional statement. For example, in people who have disease Z, as many people who take treatment X have outcome Y as those who take placebo. And this idea that science and clinical science is really about systematically excluding false propositions. And if we are able to exclude every false proposition, what we're left with is a list of true propositions. And this sort of Popperian idea that science progresses through elimination of false propositional statements. In this concept, a trial then is really a scientific experiment performed in human subjects. So this idea that you repeat this experiment many times in different subjects, and then you use statistical inference based on some assumed distribution of the data. It's commonly assumed that that trials permit causal conclusion by nature of their design. And so clinician researchers distinguish clinical trials from observational studies, which don't guarantee that causal conclusions can be made from associations. And there's this idea that clinical trials are therefore a gold standard of evidence because they permit causal conclusions. And the key features of clinical trials that grant this permission are the use of randomization, so assigning individuals to treatment by chance rather than by any other factors, and also blinding is often seen as a key tool for permitting causal conclusions to be made from evidence generated by clinical trials. But the problem with this perspective is that, and with clinical trials in particular, there are the usual problems. Clinical trials are generally very costly. There are concerns about the ethics of assigning people to treatment, even if it may be contrary to what the clinician or the patient believes is in their best interest, rightly or wrongly. There are problems around defining what sort of evidentiary threshold you need in order to exclude a hypothesis. You know, how certain do we need to be before we say this proposition is false, and also generalizability, or in epidemiology, what we typically call external validity. To what extent is the evidence obtained in the trial population allow me to make inferences about the broader population of people with particular disease? But there are more fundamental problems with this traditional perspective. One is whether it's adequate to reflect scientific knowledge as a series of propositional statements. Is science really about having a list of true propositional statements, or is that inadequate, or a list of propositional statements inadequate for defining scientific knowledge? There are also fundamental problems with average causal effects. So, in a clinical trial, which is done in a population, we imagine that in individuals who are participating in that trial, there is an effect of a treatment, and really what we're doing is finding the average effect across all those individuals participating in that trial. But then the question is, well, the average in those individuals, who does that average apply to? And how useful is it to have an average causal effect defined in a population of trial participants, and to what extent can I use that average effect in that trial population to make decisions about people with the disease who weren't involved in that trial, the idea of transportability. But another fundamental problem is that this assumption that trials guarantee that observed associations are causal is not true, and it's almost all clinical trials there's deviation that prevents us from being able to assume or take it for granted that any associations must be causal. So that's an issue with the internal validity of clinical trials. So because of these problems with this sort of traditional perspective, we take a more pragmatic perspective, which is that our ultimate objective is to improve the health outcomes of patients, and this is future patients, but to do this in an environment which is highly irregular and possibly dynamic. By that I mean, and contrast the clinical environment with, for example, in physics, where you would expect that, for example, the speed of light or the force of gravity on Earth to be constant over time, and with repeated observation, you should be obtaining the same result. You don't expect that with individual subjects participating in the trial. In fact, you expect that the effect of a treatment is not constant across all individuals. It varies, and that obviously makes it a complex problem then to be making decisions about how you should manage future patients. But in order to do this, in order to improve their health outcomes, we want to generate and learn a model of the regular features of the world, and to do that, creating models that are reliable for informing our future actions. And so really what trials are about informing the creation of reliable models of the data generating process. So what is the underlying unobserved process in the world that gives rise to what we actually observe? And we think that to have a model that is useful for that purpose, that model should be causal and counterfactual. So it should allow us to imagine a situation in which one treatment or strategy is implemented rather than another, and to consider what are the consequences of choosing to act in one way rather than another. And that's really what we're interested in those counterfactuals. That the models should be as simple as possible, but they shouldn't be simpler. And so we can have some extremely simple models which can do a lot of work for us, but to the extent that those simple models don't accurately or sufficiently reflect the real world, they may fail to become reliable models for us to base future actions on future patients. The models are necessarily subjective. They have to be informed in part by our beliefs about the world or our beliefs about the data generating process. But they should also be objective in the sense that they should be mutable in the light of observation, which means that we should be able to update our beliefs about the world in the light of what we observe, because if it's not updatable, then it's not useful as a model. And so we consider that there's a sort of a hierarchy of models that we work with. Firstly, there's the EARN model, and this is the simple model that clinical trialists probably unknowingly use whenever they implement a traditional clinical trial. So the idea is that participants in the clinical trial are like balls in an urn of different colours, and that the process of doing a clinical trial is like randomly sampling balls out of that urn and trying to make inference about the contents of the urn based on the balls that you draw out of that urn, and that's a model that in a very simple clinical trial with a complete follow-up can actually be very, very powerful, and it's the sort of the major workhorse of most clinical trials. But for a lot of real-world clinical trials and applications, I'd say most they're not perfect clinical trials, and that EARN model, very simple EARN model, falls down. It's no longer adequate. And so we then need to use slightly more complex models, and we typically start with a causal directed acyclic graph, so just a qualitative graphical model that looks to depict the underlying data generating process. And then the next step up from that qualitative representation of the process is a Bayesian network model, and we use these to start to flesh out our beliefs about the size of the effects, of the causal effects, and then ultimately we're usually working up to some kind of Bayesian statistical model that reflects the underlying causal structure of our model, and then we can, if necessary, use even more complex models like agent-based models, where you've got complex dynamics and dependent happenings. For example, in a vaccination program where the vaccination status of one person indirectly affects the vaccinations, the risk of disease or the outcomes in other people in that population. So sometimes more complex models are required depending on the underlying situation, the context. So we follow a process for building these causal models. First question is what we believe to be the unobserved disease process in medicine. We call this usually the pathophysiology of a disease that's regular to or common across all people. And then based on this, what are the things that we can observe? That's the signs, the symptoms, which are what patients report to us, or tests that could be in the form of a laboratory blood test result or a biopsy result or an X-ray result. What things give us information about the pathophysiological state of each individual? And then what are the consequences of the disease that we're hoping to either promote or to avoid? That is, what are the outcomes that we're hoping to either promote or avoid with our intervention? Those outcomes might be directly observable, like death, or they might be latent. They might be a concept of quality of life or pain or suffering or something like that. That is definitely something we want to avoid, but not necessarily something that we can directly observe. Then what's the best way to measure those outcomes of interest? So these are our endpoints. And then how and where do we believe that our treatments of interest work, and what are the other factors that are likely to affect those outcomes, and which of those factors might also modify the effect of the treatments of interest. So this is the sort of the process that we would go through with our domain experts in order to come up with a preliminary causal model of the underlying problem of interest. And so to make this more concrete, I'll give you the example of a trial that we're doing in cystic fibrosis, where I've sort of simplified several months worth of work down to make it tractable. For those of you who don't know, cystic fibrosis is a relatively uncommon multi-system disease that's inherited. It affects about 3,500 Australians. It causes progressive loss of lung function until people either die from the disease or have a lung transplant, usually at the 5th or 6th decade of life. There's sort of an implicit consensus, a disease model for cystic fibrosis that's largely agreed upon by domain experts that could be summarised in a series of propositions. The first is that the symptoms of CF and death are mostly caused by this progressive loss of lung function. The lung function in turn is caused by intermittent acute chest exacerbations, which are caused by bacterial infection of the lungs. And better management of these chest infections will cause a slowing of respiratory failure and therefore improved symptoms, and therefore delayed death or need for transplant. So when we worked with the domain experts to come up with a preliminary causal model of the problem, we started with the outcomes that they were looking to improve for patients with cystic fibrosis, and their focus was largely on improving lung function. And so we have the concept that in the context of one of these chest exacerbations, we have a person's lung function on day 0, which is the start of the exacerbation. We have their lung function a week later, and that's the thing that we're trying to improve. And the difference between the lung function on day 0 and day 7, we call that the delta, the change in lung function. We're hoping for each patient that we can maximise that gain in lung function or minimise the loss of lung function. And the belief is that by your choice of antibiotic treatment, either the type of antibiotic or the way that you take the antibiotic or the duration with which for which you take the antibiotic has a direct causal effect on the observed lung function after 7 days of treatment. But it's not the only thing that affects the observed lung function. There's also a person's baseline lung function. So people, as I described, have this progressive loss of their lung function over time. And so your lung function measured on day 7 is not just influenced by whether you take antibiotics and how you take them, but also by what your baseline lung function is. And your baseline lung function also obviously affects your lung function on day 0 at the start of the exacerbation. But importantly, it can also influence what antibiotics you take and how you take them. Baseline lung function is not the only risk factor. There's also the types of bacteria and the density of colonization of bacteria in the airway. And one particular bacteria that's important cystic fibrosis is Pseudomonas aeruginosa. Some people are colonised with it. They tend to have worse outcomes. It tends to be inflammatory and drive worse lung function. But some people don't have Pseudomonas. They tend to do better. And that Pseudomonas status obviously also therefore drives the baseline level of lung dysfunction and also lung function on day 0. And again, it can also influence which antibiotics and how antibiotics are given for management of one of these exacerbations. And then we can add to the complexity here, because the antibiotic that someone takes for an exacerbation has to be prescribed. And it's just because an antibiotic is prescribed doesn't necessarily mean that an antibiotic is taken. The taking of antibiotics depends on a range of things. Firstly, it needs to be prescribed, but also the patient needs to agree to take them, and the patient needs to be able to take them. So the patient has side effects or intolerances or other issues, they lose intravenous access or whatever it is, can mean that an antibiotic might be prescribed but not actually taken. And we can take this one step further and think about people's intentions, and think that in order for an antibiotic to be prescribed and taken, a clinician, patient have to have an intention or a plan to take that antibiotic in the first place, which is itself informed by the baseline risk factors, including things like the patient's Pseudomonas status and their level of baseline dysfunction. So that's the qualitative DAG, and then our next step in the design process would usually be to then start to populate the DAG with a series of conditional probability tables in the form of a Bayesian network. And these conditional probabilities are really to help inform the design. They can be purely hypothetical. They should be plausible. They could be informed by actual data, but for the purpose of designing a trial, they don't necessarily need to be. And so here we imagine a Bayesian network reflecting that causal diagram, where we just imagine, for example, that with regards to the antibiotic treatment, a clinician just has a choice between either prescribing the antibiotics to be given intravenously, which is relatively aggressive therapy. It requires intravenous access. For some antibiotics, it comes with a range of toxicities, so it may be reserved for those who have a worse prognosis, or it can be given by the inhaler, which is a simpler way of giving antibiotics, but may not be as effective. And so we can imagine how those various steps in the underlying disease process are related to each other. We can use the Bayesian network with our domain experts to imagine a range of scenarios. So imagine what we would observe in a person who takes intravenous antibiotic therapy rather than inhaled therapy. What would be the expected gain in their lung function? In this case, we imagine that 70% or thereabouts of people who take intravenous therapy have a large gain in their lung function. Contrasting that with people who take inhaled antibiotics, of whom only 62% have a large gain in their lung function. So on the surface, it looks as though people who take intravenous antibiotics gain more than those who take inhaled antibiotics. But of course, that is all potentially confounded by these risk factors, Pseudomonas status, baseline lung dysfunction. And so we would need to be able to adjust or control for those factors that would otherwise confound the association. And in the context of the Bayesian network and the hypothetical scenario, we can do that, and we can see that in the scenario where there is no difference between intravenous and antibiotics, that there is no difference in outcomes between those who take intravenous versus inhaled antibiotics. So
5 minutes left, Tom.
thank you. So now we can move beyond what we would observe in usual practice to what we might expect to observe in a clinical trial, where we actually now assigning antibiotics as opposed to just observing what people do. And we can imagine a situation where someone is assigned, for example, to take intravenous antibiotics, and that assignment might align with what they intended to do. That might align with, this might be a person for whom it was planned that they receive intravenous antibiotics. They get assigned to antibiotics, so intravenous antibiotics is prescribed, and because that prescription aligns with what the original intention was, there's a very high probability that that patient will actually take intravenous antibiotics, and we can observe their outcome. But we can also imagine a situation where someone plans to use intravenous antibiotics based on their known risk factors, but in fact they're assigned to inhaled antibiotics. And so the clinician might prescribe the inhaled antibiotics aligning with the treatment assignment, but because that assignment doesn't align with what the original intention was and what they wanted to do in the first place, there could be individuals who defy that assignment and still go ahead and have intravenous rather than inhaled treatment. And as a result of that, the expected gain might be different than in the situation where someone not only is assigned the antibiotics, but they're actually prescribed it and they actually take it. And so this is the difference between what we call an intention to treat effect, where there could be a discrepancy between what someone is assigned to do and what they actually do in practice, and what is traditionally called a per protocol effect, where there's perfect alignment between what someone is assigned to do and what they actually do in practice. And so that's a very simple way that we can work with domain experts to understand the problem and to understand where trial design does not necessarily guarantee a causal inference to be permitted, and what other factors we might need to take into account or adjust for in order to recover causal effects. In reality, almost every disease process is complex, and this is a more realistic model of that particular problem domain that fleshes out that detail. So just quickly, going from a BN to the trial, we use the BN to define the estimand, where the estimand is the causal effect that we want to estimate in order to make good decisions in the future. But we have to contrast that with the effects that can be estimated. So sometimes a domain expert will come to us saying this is what they want to measure, but by virtue of the way that the trial is designed, they may not be able to actually measure that specific causal effect, and the Bayesian network can help us to make those issues explicit. Help us to define the particular population and subgroups that we want to measure those causal effects in. Helps us to define specifically how the intervention is defined, and whether we're defining it in terms of intention to treat perspective, that is the effect of the assignment regardless of the treatment that's actually given, versus the protocol, which is the idea that we want to measure not the assignment of treatment, but the effect of actually taking the treatment itself, which is a more complex thing to do. It helps us to define the comparators, and also we need to work out how that causal effect will be quantified, for example, in terms of a risk ratio, risk difference. And then given all of the above, it helps us to make decisions about how we will then deal with so-called post-randomization into current events. These are things like a non-adherence to treatment, crossovers, deaths, loss to follow-up, all the things that complicate clinical trials and that prevent us from just blindly accepting measured associations as cause effects. And last slide, next step is then to hand over to the statisticians who then take that estimate from our causal model, from our Bayesian network, to define a statistical estimator. So given the estimate and the model of the underlying data generating process, what statistical model is needed to estimate the estimate? Which variables need to be included? What's the functional form of the model? What things need to be included as linear predictors of the outcome? What hierarchies need to be taken into consideration? And considerations about assumptions about exchangeability of observations, for example, allow us to translate our Bayesian network model into a statistical model, and then we use that Bayesian network model as a basis for generating dummy data, so multiple pretend participants in a trial across multiple pretend trials, but where we take the treatment effects to be fixed and known by us. And then our question is, does that statistical model, which is our estimator, recover the known treatment effects? That is the estimate. So is the statistical model fit for purpose? And then we use simulation to calibrate trial rules for satisfactory operating characteristics of that trial. So where the considerations of bias in estimation, so that's a strong consideration. We want to estimate our estimator of the causal effect to be unbiased, but that sometimes needs to be traded off about considerations of statistical efficiency and precision, but also considerations about human suffering. So, and I think that's something that we bring to the design of clinical trials, is not just thinking purely from a statistical perspective in terms of unbiased estimation, but also what is the cost of unbiased estimation? Should we be willing to compromise on bias in order to optimize the outcomes and limit the suffering and burden on participants who are participating in trials? And by that I mean potentially stopping trials early, or stopping trials for success or for futility, where that can come at a cost of a bias in our estimation, but we think that's justified because it prevents needless burden and suffering.